Let's talk about concentration. So if we have these two beakers here, and I'm dissolving this blue solute in this purple solvent, and I look at this beaker here, I would say that this beaker is very concentrated in solute compared to this one. The volume's not as high, so there's not as much solvent, but the solution is more blue, which tells me that there's more solute. So this would be a very concentrated solution compared to this one. This solution would be considered more dilute. It has a higher volume of solvent, the water level on the beaker is higher, and it has less solute. The blue is not as dark as the other beaker here. If we could look at these solute and solvent molecules under a microscope, you could see that in this picture here, we have a lot more of the blue solutes than these purple solvents, which is why it looks bluer. And in this particle diagram here, we have a lot more solvent particles than we do these blue molecules, which is why it looks less blue. This is a very qualitative way to discuss concentration. Saying one solution is more or less concentrated than another doesn't really tell us that much information. For that, we need something quantitative. We need a value, a measurement called molarity. So molarity is a very common unit of concentration in the science lab, in the chemistry lab. So the formula for molarity is on table T. You don't need to memorize it, you just need to know how to use it. So molarity of a solution is the moles of solute divided by the liters of solution. Now it has to be moles over liters, and unfortunately they'll probably never give you moles and liters. This is a little too easy of a math problem. They'll give you like grams and milliliters, and you'll have to do some conversions. I'll go through all the different possible ways that I've seen these questions asked on the Regents in these next couple of example questions. So when you're done, the unit is a capital M. For example, 6.0 molar is how you would say the molarity of that solution. So here's an example problem. What is the molarity of a solution that contains 0.45 moles of sucrose and 500 milliliters of solution? So we'll rewrite the formula, moles over liters. So they say we have 0.45 moles, and we need to divide that by liters of solution. The problem is they didn't give us liters, they gave us milliliters. So we need to do a conversion. 500 milliliters, and we'll set up a bracket. I need to know the relationship between milliliters and liters. Well, there's 1,000 milliliters in 1 liter. So my milliliters will cross off, and it will leave me with liters. So I need to do 500 divided by 1,000, and that, of course, is 0.5. If you do enough of these, you'll probably memorize this conversion factor, and you can do this in your head. But until then, don't worry about doing a little bracket conversion problem for any of these. So our math is 0.45 moles divided by 0.5 liters, and that is 0.9 molar. Next, intravenous IV saline solutions are often administered to patients in the hospital. One saline solution contains 0.90 grams of sodium chloride in exactly 100 milliliters of solution. What is the molarity of this solution? So remind ourselves of the formula again. Our formula is moles of solute over liters of solution. Now they didn't give us moles and they didn't give us liters. So they didn't give us anything that we need for this formula. But they gave us something. They told us grams of salt and they told us milliliters of solution. So what we need to do is to convert our grams of salt into moles of salt. And this should be no problem for you at this point. So I have 0.9 grams of NaCl. To convert that into moles of NaCl, I need to know how many grams I have in 1 mole. So in 1 mole of NaCl, I have the weight of 1 atom of sodium and 1 atom of chlorine. And you get those right off the periodic table. And if you round up, you get 58 grams of NaCl. So our grams and grams will cancel. 0.9 divided by 58 is 0.016 moles. And you can plug that in up top. And then next we need to convert 100 milliliters of solution into liters. So 100 milliliters, we'll use our conversion factor, 1 liter over 100 milliliters, or 1,000. 100 divided by 1,000 is 0.1, or you can just move that decimal 3 places to the left whenever you're dividing by 1,000. So 0.016 moles divided by zero point 0.1 liters is 0.16 molar. Here's another one. How many grams of NaOH are needed to make 1 liter of a 3 molar solution? So our formula again is moles over liters, and they want us to solve for grams of NaOH. So that's our solute. We're dissolving NaOH in water, presumably. So we need to work backwards here. First, we need to figure out how many moles we need, and then convert from moles to grams using a conversion factor. So I want to make a 3 molar solution, and I want to make a liter of it. So I need to know how many moles I need to do that. So we can just cross multiply here. 1 multiplied by 3 is 3. So I need 3 moles of NaOH in 1 liter to make a 3 molar solution. Now I need to figure out, well, how many grams of NaOH that is. So I'll take my 3 moles of NaOH and I'll multiply by its molar mass off the periodic table. NaOH contains the mass of 1 sodium, 1 oxygen, and 1 hydrogen. If you look that up, that's about 40 grams. So 3 times 40 is 120 grams of NaOH. So we can qualitatively describe the concentration of solutions with words like concentrated or dilute. One common way to quantitatively describe the concentration of a solution is to calculate molarity. Now, there's a bunch of other different types of concentrations. In Regents chemistry, we only deal with molarity and parts per million, which we'll be talking about in the next video. The formula for molarity is on table T. You don't need to memorize it, you just need to know how to use it. It's the moles of solute divided by the liters of solvent. Unfortunately, like you saw, they rarely ever will give you straight moles and liters. They just ask you to divide these two. You're going to have to do some conversions to get to moles and liters before you do your math.